than this for L'Hopital's rule. So when we plug in, in limit as x approaches 0 from the right, from 1 plus sine 3x raised to cotangent x. When we plug it in, so when x approaches 0, this approaches 0. So this will be 1. And cotangent, remember cotangent is cosine over sine. And on the right-hand side of 0, this is 0, positive, and this is 1. So this will be 1 raised to infinity. So it's one of the powers, and it's ugly, of course. Good, so I have no choice but denote the function by y. And then apply natural log and get cotangent x times natural log of 1 plus sine 3x, as most of you started. I mean, I think everyone started like that. And then I have to apply the limit to both sides. So I have limit of natural log y as x approaches 0 from the right equals limit of natural log of 1 plus sine 3x divided by tangent x if x approaches 0 from the right. Because tangent is 1 over cotangent. So I saved a little bit of time because now the numerator, it goes to 0, and the denominator goes to 0. So tangent 0 is 0. Yay! So in just 1 step and a half, maybe 2, I managed to change it into something that I can apply L'Hopital's rule to. So this is limit as x approaches 0 from the right. The top is 1 over 1 plus sine 3x times cosine 3x n times 3, and everything divided by secant squared x. So when x approaches 0, this is 1, this is 1, this is 0, so then the answer is 3. Now, remember, you have to copy the beginning and you have to copy the end. So when I copy the beginning and I copy the end, now, because everything is continuous, I'm allowed to swap the operators. So limit of y as x approaches 0 from the right is 3. And obviously this cannot be anything else but e to the third. Bring 3 in front, and natural log e is 1, so you get 3. So therefore the limit, of 1 plus 3x raised to cotangent x when x approaches 0 from the right is e to the third. So remember the assessment at the very end. When you swap the operators, you have to make an assessment on what can it be. So never forget this step, right? Because if you don't copy the beginning and copy the end, then it may be difficult to understand what's happening next. So once you copy the beginning and the end, then you're done. Very good. Any questions? Okay, so any questions from me on anything? Anything? I need more paper. Any questions? Okay, so the last 6 sections of this chapter, of this course, are part of test 4. So what we start from tonight on will not be tested on test 3. It will be part of test 4. Are you okay with that? Yes? Okay, we start with 4.9, antiderivatives. And you'll understand why I insist that 4.9 is part of chapter 5, not a part of chapter 4. Let's suppose we are given the velocity. Given. How will I determine the function that gives us the distance? Moving backwards. So now I'm given the derivative, right? So this is basically s prime of t. How do I go back and find the function whose derivative is that? I find the antiderivative. Very good. So, two possible situations. And you could say, does it make such a big difference? Yes and no, depending on the situation. So the notation is very important. Given f prime, find f. So given the first derivative, and I find the function, if I'm given the notation f prime, then I have to use the notation f. Given f, I don't specify the derivative, but it's a derivative. Find uppercase f. So again, is this such a big deal? It's important. So if the notation of the function is denoted that I'm given is denoted by f prime, and I want to go backwards and find the function whose derivative is this, I have to denote it by lowercase f. If I'm given a function f and I'm asked find its antiderivative, then I have to denote it by uppercase f. Okay? In both cases, these are called antiderivatives. They are both the antiderivative. However, the notation is important. Okay, so now let's look at the power rule for a moment. If you remember, when we differentiated x to the third, we got 3 times x squared. Agreed? Now I want to go backwards. If I'm given, for example, x to the fifth, the question is, which function prime is x to the fifth? Divided by 6, indeed. Indeed. You bring down 6, you cancel 6, you subtract 1 from the power, and you get x to the fifth. So in general, we say that x to the nth is which function prime? X to n plus 1 over n plus 1. We bring n plus 1, we simplify, and we get x to the nth, subtracting 1 from the power.
Plus c.
Yes, for the most general, yes. Yes. So let's consider that as well. The most general antiderivative, for f prime, it will be f of x plus a constant c. And for f, it will be uppercase f of x plus a constant c. So if we are given f prime, the most general antiderivative is f of x plus a constant c. Why? I have to show that when I differentiate this, I get this. Yes, of course, when I differentiate this, I get f prime and c prime is 0. When I differentiate this, I know the notation is different, so the derivative of this is f. When I differentiate c, I get 0. So this is the most general antiderivative, where c can be any constant. C, any real number. C can be any real number. So I would like us to practice, and I'd like to start with the velocity, acceleration, etc. So let's look at an example. You can choose, of course. A particle is moving with the given data. Find the position of the particle. I would like to choose something maybe with the acceleration, because the velocity is just one step less. So what if we just start with 62? Okay. And 62. On page 349. We have A of t equals 3 cosine t minus 2 sine t. And we are given two conditions. S of 0 is 0 and V of 0 is 4. Disregard these for a moment. We're asked to find, one more time, the particle is moving with a given data. Find the position of the particle, which means the function that gives the distance or the position. Same thing. Okay. So in other words, we are going backwards. We want to find V of t. The acceleration is the second derivative of the distance. The velocity is the first derivative of the distance particle, or the distance of the particle, right? Or the motion formula. So here's how we proceed. We want to find a function whose derivative is 3 cosine t. Which function prime will be 3 cosine t? 3 sine t, indeed. When I differentiate 3 sine t, I get 3 cosine t. Now, I'm asking myself which function prime will be negative 2 sine t. Positive 2 cosine t plus, I'm going to call it C1. Okay, I see that I am given a piece of information. What do you think this is given to us? It will help us, or it will enable us to find what? C1. Exactly. So V of 0 is 4, means 4 equals 3 sine 0 plus 2 cosine 0 plus C1. But how much is sine 0? Good. How much is cosine 0? 1. So then the equation is 4 equals 2 plus C1. We know C1. 2. I go back and rewrite the velocity. Okay, so the velocity v of t is 3 sine t plus 2 cosine t and plus 2, of course. I just determined it. Plus 2. So now we can go back and finally determine the motion formula or function. So S of t. Which function prime is 3 sine t? Plus, which function prime is 2 cosine t? Which function prime is 2? Excellent. Plus C2. I do have a piece of information that says S of 0 equals 0. Why is this given to us? To find C2. So then this is 0 equals negative 3 cosine 0 plus 2 sine 0 plus 2 times 0 plus C2. Sine 0, 2 times 0, cosine 0. So 0 equals negative 3 plus C2, which makes C2 equal 3. Therefore, we did determine the motion formula. Negative 3 cosine t plus 2 sine t plus 2t plus 3. And this is unique to the given conditions. No other function fits the given information. Any questions? Any questions? Okay, let's choose now from any functions. Anything you want. So for example, 44, maybe 40. Since we looked at sine cosine, now we can determine 47. Anything. Which one? 41. It's sine and cosine again, but that's okay. I think we should look at 43. 43. The second derivative equals 4 plus 6x plus 24x squared, and we are told f of 0 is 3 and f of 1 is 10. Okay, we're asked to find the derivative. We're asked to find the function given the second derivative and two conditions. What do I have to determine first? Excellent. Which function prime is 4? Plus 6. I increase the power by 1 and divide by that number. Plus 24. I increase the power by 1 and I divide by that number. And plus C1. Any questions so far? Is this okay? Okay, we clean it up a little bit. So f prime of x, and put it in descending order. 8x cubed plus 3x squared plus 4x plus c1. I don't have any information about the first derivative. I can't do anything. I have to move on. I can determine c1. Not just yet. Good. So now please dictate what you will write for the function. Last night I forgot to scan from yesterday, and I got an email from one of my students. The notes are not up. I said, I'm so sorry.
Well, at least someone's using them.
Yes, so I have to scan all this. So 2 classes yesterday and 4 today. I just forgot last night. Good. So then 8. I increase the power by 1 and divide by that number. Plus 3. I increase the power by 1 and I divide by that number. Plus 4. I increase the power by 1 and divide by that number. Which function prime is c1? c1x plus c2. Now, I do have 2 pieces of information. I'll copy them here one more time. F of 0 is 3, and f of 1 is 10. And that's exactly what I need because I have 2 variables in function f. I have c1 and I have c2. Okay, so let's start. We want to simplify first. Yes, I agree if you say that. So this is 2x to the 4th plus x to the 3rd plus 2x squared plus c1x plus c2. That's what I have so far. So now I plug in 0. 0, 0, 0, 0. So this is 3 equals c2. So now the function is 2x to the 4th plus x cubed plus 2x squared plus c1x plus 3. Now I have to use this piece of information where the left-hand side is 10. And what do we have on the right-hand side? Plus c1, yes. 2 plus 1 plus 2 plus c1 plus 3, correct. So this is 4, 6, 8 subtracted from 10. C1 is 2. So then we discovered the entire function. And this is the unique function that fits the information given, that has the second derivative that were given initially, and fulfills the given conditions that f of 0 is 3 and f of 1 is 10, and there is no other such function. This is the only one. Any questions? Any questions? Anything? Okay, I would like to look at the word problem and see how this is helpful and why. Something that we've seen before. A company estimates that the marginal cost in dollars per item of producing X items is this. So the marginal cost is what, basically? What is the definition of the marginal cost? And this is 71 on page 350. What is the marginal cost?
Cost required to.
Right, but the derivative, that's all I wanted you to say. The marginal cost is the derivative of the cost function. So this is given to us, very easy and simple, 1.92 minus 0.002x. If the cost of producing one item is $3.56, if the cost of producing one item is $562, what is this? Right. Yes, meaning C of 1 is $562. It says, find the cost of producing 100 items. So we're asked to find this. But I don't have the function yet. So what do you recommend we do? Yes, so let's find the cost first. Perfect. 1.92x minus 0.002x squared over 2 plus c. Perfect. So you can simplify it a little bit. So c of x equals 1.92x minus 0.001x squared plus c. And we're given that c of 1 is 562. So 562 equals 1.92 minus 0.001 and plus c. How much is c? $562 minus 1.92, but plus 0.001. I got 560. Careful, I don't want you to confuse. So this is the little c. So this is the little c. I should have not used c. Let me use d, not to be confused with anything. Because this is the cost, this is c. Let's say little d. I got 560.081. So therefore, the cost function is 1.92x minus 0.001x squared plus 560.081. And now and only now we can find the cost of 100. So C of 100. So we will get 1.92 times 100 minus 0.001 times 100 squared and plus 560.081. So it's 192 and plus, I move 4 decimals, so this is not plus but minus 10, and then plus 560.081. I got 742.081. Please correct me if I'm wrong. Let me know if that's correct.
Yeah.
So C over 100, I got 742.081. Any questions on, these are just the basics, that's all I really need, of finding antiderivatives. This is extremely helpful in the next chapter. Okay, before we start chapter 5, I want to refresh your memory on something very important. Let's suppose we're given f of x equals x to the 4th minus 3x squared. I would like you to give me two things. I would like you to give me f prime, and I would like you to give me dy. This is the derivative of f, and this is the differential of f. So please give me the first derivative for this function. Okay, please, I forgot, sorry. 4x to the 3rd, and this is it. What about dy? What is dy? It's not the same with f prime. So 4x cubed minus 6x.
Times dx.
Very good. Please remember that. We've had this problem on, similar problem on the previous test. So please make sure you understand the difference between the two. The derivative is one thing, the differential is a different thing, because I need to use this in this chapter and moving forward, okay? So this is the differential and this is the derivative. The differential, one more time, is f prime of x dx. Okay, chapter 5. I don't want to put the title because it takes me a while till I get to the title. So for now, it's just chapter 5. So in 5.1, I would like to look at areas. And you can say, what is that? What are you talking about? In a minute, you'll see. So our first task is to find an approximation of the area under f of x equals x squared between, of course, between the function and the x-axis, between 0 and 2. Find an approximation of the area found under the graph of x squared between 0 and 2. This is our first task. Okay, I'm going to graph. This is 1, this is 2, 1, 2, 3, 4. This is the graph. This is the graph of y equals x squared between 0 and 2. When x is 0, when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. The area under the graph between the x-axis and the graph is obviously this. Okay. The first step, we're going to use 4 subintervals. And we have 3 possibilities. So we want to find an approximation or approximate the area under the graph of x squared between 0 and 2 with 4 subintervals. And we have 3 options. We're using the leftmost point of each subinterval. Using the, what do you think? Right. Most point. And the last one, using the midpoint. Not the left, not the right, but exactly in the middle. Okay, what is this? We will denote the first one by uppercase A, left 4. We will denote the next one with uppercase right 4. And of course, uppercase mid 4. We're going to use these notations. Okay, first I go back to the graph to create 4 subintervals of the same width. And we're going to use the leftmost point, rightmost point, and the midpoint to estimate the area. Okay? So this is 1. Right here in the middle, 0.5. Right here in the middle, 1.5. I created 4 subintervals. This is 1. This is the other. This is the third. And this is the fourth. 4 subintervals with the same width. Now, the height. We're going to talk about the left. This graph is only for the left. So we're going to determine the area for left 4. I can't use the same graph. I have to create another graph for the other 2. So the area of this, we're going to create rectangles. But the height is the leftmost point. So there is no height. Height is 0. So base times height, 0.5 times the height is 0, is the area of the first subinterval. In the next situation, this is the height of the leftmost point. I draw a horizontal line, so this will be the area of the second subinterval. The area of the third rectangle will be, this is the height, the leftmost point, so this will be the area of the third piece. And the last one with the leftmost point is this area. We have 4 areas, sort of. The first one is 0, but it doesn't matter. We still have 4. Do you think that the area approximating this particular graph, the area of this particular graph under the graph between the graph and the x-axis, do you think it's going to be an underestimation or an overestimation of the actual, correct, exact area? Right, because there's some holes in there. It will definitely be an underestimation. It will be actually the lower bound. So let's determine this. So the area with the left using 4 subintervals is an approximation, but it equals the width of each subinterval times the height of each subinterval. And of course, this will be a sum. Sum of width times height. Okay, so here's the first one. Base, 0.5, times the height, 0, plus base, 0.5, times the height. But the height is f of 0.5. So f of 0.5 plus. The next subinterval, the height is f of 1. So plus the base times f of 1 plus. Can anyone give us the area of the last rectangle using the leftmost point? Base is still 0.5 and the height is? Very good. So 0.5 times f of 1.5. Okay, so we determine this is 0. I will factor out 0.5. And then I have f of 0.5, which is 0.5 squared, plus f of 1, which is 1 squared, plus 1.5 squared. I factor out 0.5 because it's the same for all of them. And then I have 0.5, and in parentheses 0.25 plus 1 plus this 15 squared is 225, so this is 2.25. So 0.5, 2.25 plus 0.5 is 2.5 plus 1 is 3.5. So this will be, so with 2 decimals, 1.75. So this is the area, the estimated area, using 4 subintervals of equal width and the leftmost point of the interval. Any questions? We will repeat 2 more times. Okay, I need a new graph. 1, 2, 3, 4, 1, 2. This is 1 point, this is the other. I graph the same function 1 more time. Oops. This time, we divide the interval between 0 and 2 into still the same 4 subintervals. But this time, we're going to use the rightmost point. Okay, so here is the first area, or rectangle. Here is the second area, or rectangle. Here is the third area, or rectangle, if you want. And here's the last one, with the rightmost point. This one with the rightmost point height, this one with the rightmost point, this one with the rightmost point, this one with the rightmost point. 0.5, 1, 1.5 is the same. What do you think about the area with the rightmost point for this function? Okay, it's not going to be the same for all functions. So for this function, what would you say? Would it be an underestimate or an overestimate of the actual exact area under the graph? Right, because there are these pieces that are completely outside of the area. Good. So then will be, of course, 0.5 this time times f of 0.5 plus 0.5 times f of 1 plus 0.5 times f of 1.5, and finally plus 0.5 times f of 2. I will again pull out 0.5. F of 0.5 is 0.5 squared. F of 1 is 1. F of 1.5 is 2.25, and f of 2 is 4. I add those up. So 2.5 plus 5, 7.5. Correct me if I'm wrong. I multiply 35, 37, 2 decimal digits. This is the area, which is the upper bound, an overestimate of the exact area. Do you think that the third one will be lower than 1.75 or greater than 3.75 or in between the two? Of course, of course. So let's take a look. And of course, it will be the best approximation of the exact area using 4 subintervals. Okay. Now I have to use the midpoint, and I draw the height. I use the midpoint, and I draw the height. I use the midpoint, I draw the height, and I use the midpoint, and I draw the height. So the area, so remember this is 0.5 and 1 and 1.5 and 2, but now this is 0.25, this is 0.75, this is 1.25, and this is 1.75. Those are the midpoints. So the area with mid 4 will be still 0.5 multiplied by f of 0.25 plus still 0.5 base times height multiplied by f of 0.75 plus 0.5 times f and 1.25 and plus 0.5 times f of 1.75. Again, I will pull out 0.5 because it's the same in all. And then I have 0.25 squared plus 0.75 squared plus 1.25 squared plus 1.75 squared. What I recommend with this, again, it's up to you, but allow me to recommend. Here's how I would approach this. It's not the only way. So go to Stat and press Enter because we want to edit. So if I edit list L1 in this case is this just the x values. 0.25 is the first one. 0.75 is the next one. 1.25 is the next. And 1.75 is the last. Enter. So we have 4 midpoints. Highlight L2 now. Go to the right and up to L2. So what are we entering in L2 is this. The base 0.5 multiplied by list L1 squared, because that's our function. So we want to multiply base times height, and that's all we do. The function is x squared, that's why I put L1 squared. When I click enter or check or press enter, I get all those values already multiplied. Which values? One more time, I'll go back for a second. I will get this as the first entry in L2. I will get this as the second entry in L2. I will get this in third, and I will get this in the fourth. So now I want to add them up. Here's what I do. I go to Stat, to Calculations, one variable stat on L2, second and 2, and just click on Calculate. The answer is this sum, and I'm getting to that notation in a minute. The sum of all those in L2 is 2.625. Do you have to do this? No. I think it's the easiest though. So the answer is 2.625. Well, obviously, as expected, this is the best approximation. So the area with the left 4 is less than the area with the mid 4, and is less than the area with the right 4 for this particular function. So we obtained, the first number was 1.75. This one is 2.625, and the last one was 3.75. Exactly as you expected. I have a couple of questions before we look at a very important notation and work with it. What if now I use, instead of 4 subintervals, let's say I use 8 subintervals? Do you think the approximation will be better?
Yeah.
Of course. What if I jump from 8 subintervals to 16 subintervals? Would the approximation be better? What if I jump to 32 subintervals?
Use an infinite number of intervals.
Excellent. So what am I getting at? There is a very important concept from our course that we work with constantly that represents what I'm getting at. What is that concept? In chapter 2, we talked about limits. In chapter 3, about derivatives. In chapter 4, applications of differentiation.
Integrals.
What am I getting at? So I'm making the number of subintervals from 4 to 8 to 16 to 32. Of course. Of course. This is the concept of the limit. I'm increasing and increasing and increasing, and I want to find the limit. So if the number of subintervals will increase to infinity, are you certain that you're going to get the exact area, no approximation whatsoever? Absolutely. If the number of subintervals grows to infinity, we're definitely going to get the exact area. There is no discussion there. Before we get to that concept, we need to go to explain what this represents. This is called the sigma notation or the summation notation. First of all, what is it? It's basically S from sum, but it's the Greek letter S. And you'll say, why don't we use S and we use the Greek letter S? This is the sum, right? Only because of convenience. And you will see why in a minute. So let's say I want to add 1 squared to 2 squared to 3 squared dot 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 to n squared. I don't want to write it like this. It's too long. I want to write it like this. I'll explain every piece of it. First of all, this indicates the fact that we are adding terms. The first term plus the second term plus the third term plus the last term. This piece says, what am I adding? When I is 1, which is the index of the summation, 1 is the lower limit, n is the upper limit of the summation. When I is 1, I get 1 squared. And then the sum says plus. When I is 2, I get 2 squared. And the sum says plus. When I is 3, then I have 3 squared. And then plus. Where do I end? Where is the last term? When I get to the upper limit. The upper limit says I is n. And that's the last term. And this is an elegant way of writing that summation. Okay, so one more time. We know that sigma or summation notation means, what is this? I is the index. We like to use I, J, or K as the index. Can you use P and T? Yes, you can. But normally we use I, J, and K. 1 is the lower limit. This is where I starts with 1. And n, lowercase n, is the upper limit.